concentration. So what is the pH of a 0.04 molar solution of sulfuric acid? Well, the first thing you'd have to know is that sulfuric acid, it's H2SO4, and when you put it with water, okay, it's going to donate one of its hydrogens to water, and it's going to turn water into the hydronium ion, and then plus we're going to have the HSO4 minus 1 ion left over. Now, H2SO4 is a strong acid. Alright, so basically strong acids are known to be strong because of pretty much 100% dissociation. So all 0.04 moles of the H2SO4 molar solution of it, all of it's going to turn into the H3O and the HSO4 minus. So if this is 0.04 molar, these are going to be 0.04 molar because there's a 1, if you balance this equation, it's a 1-to-1 ratio. Alright? Anyway, alright, because of that, you can just take this equation that pH is equal to the negative log of the H plus, and remember that H3O plus is the same as H plus, and so you can just put in that the pH is equal to the negative log and plug in 0.04, and then you would end up getting that the pH is equal to 1.4 molar. Okay? Now, that's that problem. That was for a strong acid. Okay, now let's look at this problem here. Okay, so now here we have acetic acid. Acetic acid is CH3COOH. And when you put it in water, it donates its hydrogen, and so it's going to end up making CH3COO minus because it gave away one of its hydrogen, and the hydrogen is going to go to the water and make H3O plus. Okay? Now, this initially is 0.010 molar, but this is a weak acid, and weak acids only dissociate partially. So, at equilibrium, you're not going to have all of this 0.010 molar change into 0.01 molar, this and that. So you got to do an ice table. So make an ice table. That's supposed to be a C and E. Alright? Alright. Now, so what happens is when you mix this with water, some of this is going to decrease. We don't know how much it's going to go down by, but we know that it's going to go down by minus x. And so at equilibrium, we're going to see that it's decreased by 0.010 minus x. Water, it's not going to be part of the equilibrium expression, so we're not going to worry about it. Initially, we have 0 of this and 0 of that. Now, if this goes down by x, since it's a 1-to-1 mole ratio, this is going to go up by x. And this is also going to go up by x. And so at equilibrium, we have x of this and x of that. Now, we can write the expression, and we can say that Ka, since this is an acid, is going to equal our CH3COO minus times the H3O plus divided by the CH3COOH. Plugging in the numbers, well, first you're going to have to be given the Ka of acetic acid, and it's a pretty small number because it's a weak acid. So the Ka for acetic acid equals 1.76 e to the minus 5. So now if we plug all the things that we know into this expression, we get 1.76 e to the minus 5 is equal to CH3COO, which is x, and then H3O is also x, so we got x times x, which later we'll show that that's x squared, and that's going to equal 0.010 minus x. That's supposed to be a 1 there. That's a 1. Okay. Now, anyway, because this is such a small Ka value, we can disregard this x. It's not going to really make a difference. So we can kind of simplify things by getting rid of that. So we can simplify, and we'll get 1.76 e to the minus 5 is going to equal x squared over 0.010. And solving for x, we then get that x is equal to 4.2 e to the minus 4. Now, I never really round my calculator when doing all this, but on paper, I just write it down. It gets to be 4.2 e to the minus 4. Then what we can do is we can plug that into this right here. If we know that x is 4.2 e to the minus 4, we know that our H plus, or H3O, is 4.2 e to the minus 4. So what we can do is we can just go back to our pH formula and say that pH is equal to the negative log of our H plus, which is the same as H3O. So we can just plug the 4.2 e to the minus 4 into this right here, and we end up getting that our pH equals about 3.4. Okay, that's how to do it for a strong acid and a weak acid. So notice the difference. With the weak acid, you have to use an ice table and use the Ka expression, whereas with a strong acid, you just can go ahead and take the molarity of your solution and plug that in for H+. That's it.